Okay, I think I'll start. So, um, this Thursday, the last lecture is going to be on just some introduction about NP-complete problems. So there will not be live lecture. There will only be Dr. Eldridge's recorded lecture online. And now, for those of you who want to take the redemption for midterm 1 or 2, redemption, the final is the same time as the final exam, which is actually going to be on the Saturday. So this Thursday, the class time, I convert that to the office hour. You have questions, okay? The final super homework is will be out and will be due. I believe it's next either Wednesday or Thursday. I forgot. So you would have time. It's after the final exam time. It's different from the final exam time. Okay. All right. Now, so today we want to continue to talk about the minimal spanning tree. Now, in particular, remember that for this, we're now talking about weighted but undirected graph, okay? And the last time we talked about what is the spanning tree of this graph and what is the spanning tree with the smallest total weight called the minimum spanning tree, okay? And last time we introduced this Prim's algorithm to compute the minimal spanning tree in time complexity, which is basically v plus e, the total size of the graph, times log of v, okay? And the idea behind the Prim's algorithm, it's a greedy algorithm. There's a lot of similarity to the Dijkstra algorithm we've seen, okay? In fact, the framework of the algorithm are very similar to the Dijkstra. The only way is that how we update the edge. Okay, so today we're going to talk yet another greedy algorithm to compute the minimal spanning tree. This algorithm is called Kruskal's algorithm. Okay, and then one nice thing about this algorithm is that it's also related to one popular algorithm for producing so-called hierarchical clustering for a set of points. Okay, so we'll see that later. Okay, so first let's see what is the Kruskal's algorithm. Hold on for a second. Yeah. All right, so recall that our input is a weighted undirected graph with weight function omega on the edges, okay? And the algorithm will just output the edges in the minimal spanning tree, okay? Now remember that a tree connecting V nodes would have V minus 1 number of edges, okay? So a minimal spanning tree is a spanning tree connecting all the nodes in the graph G. As such, there are basically V minus 1 number of edges, okay? And also it's a tree, means that there's no cycle, okay? So our goal here is to find basically this V minus 1 number of edges that constitute the minimal spanning tree to connect all the nodes without any cycle, okay? All right, as we mentioned last time, there are actually a whole family of greedy algorithms to do so. The intuition is that you're going to grow the tree edge by edge. You're going to add one edge each time. Every time you're going to connect to a new node, okay? And every time you want to choose a so-called safe edge, okay? In the sense that assuming currently what you haven't made any mistake yet, all the edges you collected so far from a partial minimal spanning tree, okay, a subset of some minimal spanning tree, you want to pick another edge that you know for sure would also be in the minimal spanning tree, okay? So you call that a safe edge, okay? And if you remember last time, the Prim's algorithm, okay, essentially it's that we start from any vertex, okay, any nodes, graph nodes, and I start to grow a partial connected subtree, okay? And every time in the Prim's algorithm, we have a collection of nodes we already visited and a collection of nodes we have not yet connected, okay? The safe edge we choose there is basically the minimal weight crossing edge between the visited and unvisited nodes, okay? So that's the choice made by the Prim's algorithm, and it turned out that that's sufficient to guarantee that the algorithm is correct. You compute a minimal spanning tree this way, okay? So what we're going to talk about in the Transpose algorithm, the way we choose the safe edge will be different, okay? And in particular, different from the Prim's algorithm. Prim's algorithm, we just draw a picture here. You start from a nodes, and then you always can grow a partial tree. And at any moment, this is a nodes you already visited, and you have a bunch of nodes you have not visited, and you find the min weight crossing edge. Okay, very similar to Dijkstra algorithm. So there, what we already computed is always a subtree, okay, rooted at U, okay? So in the Kruskal algorithm, we're just going to keep collecting edges. These edges may not form a single connected tree, okay? But in the end, it will connect everyone, okay? So we don't grow a connected tree anymore, okay? So we're just going to look at, keep adding edges. That's to keep the cost low while still make sure there's no cycle. That's the idea, okay? Okay, so now recall that the last time, suppose this is the input graph we're given, okay? So how do we find a safe edge, okay? If this is what we're given, well, then I know that if I look at the edge with the smallest weight, okay, in some sense, this edge is safe to add. In other words, I'm going to have minimal spanning tree contain this edge, okay? Intuitively, the reason is that if you give me a spanning tree that does not contain this minimal weight edge intuitively, okay, then what I can do is that means that adding this edge would form a cycle. What I can do is that I can add this edge in and then remove some edge from the tree you give me and still have a spanning tree while now my new tree has a lower weight. Okay, so this minimum weight edge in the tree is kind of a safe edge to add at the beginning. Okay, and suppose that we do that and we add this one to output that. I first added this one to my minimum spanning tree, and I want to continue to grow this tree at edge by edge. Okay, which one would be the next edge that is safe to add? Okay, so that's a question. Okay, all right, and well, so since what we are looking for is number one, we want to keep the cost low as possible because we're looking for the minimal weight spanning tree. Okay, in other words, intuitively, I want to add the cheap edges first. Okay, so like the edge one with weight one, this one is very cheap. It's the cheapest, has the smallest weight. Okay, so since I want to keep the total spanning tree cost low, I want to add the smallest weight first. Okay, but at the same time, I cannot just keep adding smallest weight. I also have to make sure when I add them as I grow my tree edge by edge, if any moment I add an edge, it causes a cycle, then it's not a tree anymore. Okay, so I need to throw it out. Okay, so this gives me an idea. Okay, so maybe the way that I'm going to create this minimal spanning tree is that I'm going to inspect all the edges from small to large weights. Okay, so in ascending order, so from small to large weights. I always try to first add the smallest weight possible. Okay, and when I add that edge in, if it's connect a new node, great, I keep this one because that means that I now grow, I connect more nodes, I'm growing my tree, okay? If that edge creates a cycle, that means that even though this edge is good, has a low weight, but I don't need it anymore. I already have ways to connecting them. This is redundant edge, okay? Because a tree cannot have cycle, so I throw it out, that's it, and then move on to the next edge. Okay, so that's the entire algorithm. It's a greedy algorithm. I'm just going to add the tree edge one by one from small to large weights. Okay, you want to always try the cheap edge first. Okay, and as long as it doesn't cause a cycle, then we add it to the tree. That means that because you are trying the cheapest edge first, that means so far this is the best way to grow your tree. Okay, so that's an idea. Okay, all right. So let me actually. This is what I just said. We'll add the edge gradually in a greedy manner from small to large weights. Okay, while maintain that we'll have so far does not have cycle. This is just to make sure that we have a tree. Okay, all right. Now, in fact, let's first look at an example, and then we'll come to this. Okay, let's look at the previous example. Okay, so what does it mean? The strategy on this graph. Okay. So I'm going to look at all the edges from small to large, okay? First, I look at the edge, smallest one is this one with weight 1. Clearly, by adding this one, so right now my MST, so minimal span, the tree that I'm growing are going to be blue colored, okay? So this one right now, so far, this is the only edge I found. There's no cycle in what I found so far. Okay, so I add this. Okay, the next edge, I find the next cheapest edge to add, and that's V1, V2, which has weight 2. Again, this one doesn't form any cycle, so I'm happy to add this. This is another cheap edge. Well, by adding that, I kind of reduce the number of components, connect components, right? So every time I add an edge, I reduce the number of connect components. I connect to a new node, so the number of connect components reduced by 1. Okay, so there are altogether 9 vertices. At the beginning, I have 9 connect components. After I added the edge V6, V7, I have only 8, because these two now become 1 component. And after I add the edge V1, V2, I have only 7 components, because these two also become 1. Okay? All right. So the next one we add will be the next cheapest edge. This is weight 3, and I have 2 here. Okay, let's follow the convention that let's say that I always look at the one with smaller vertex index first. So in this case, that means I'll first add V1, V6. Okay, still this one doesn't form a cycle. It again reduces the connect component. So I added this, no problem. Okay, the next one is the other weight 3 edge, which is V4, V7. Okay, now the next edge, the weight, smallest weight will be weight 4, and we have 2 edges, V4, V6, and V7, V8. Okay, and when we look at the V4, V6, when we inspected this edge, okay, now this is the next cheapest weight edge to add. I would like to use as cheap as possible. However, if I added this edge, then it forms a cycle here. Okay, so the blue are the what we computed so far for minimal spanning tree, and this causes a cycle in that. That means I cannot have this because we're looking for a tree which does not have cycle. Okay, so we do nothing to this. So the blue is not minimal spanning tree edge. Okay, then we inspect the next one, V7, V8, and this one doesn't form any cycle. As such, this one will be added to the minimal spanning tree. Okay, so we continue this way. The next edge to add will be weight 5. But when we look at V2, V4, again form a cycle. So this one we don't add. However, V4, V5 is safe to add. Okay, and the next one, next edge to inspect will have weight 6, V3, V9, and when we add it, we don't cause any cycle, so we add it, no problem. The next one is V5, V8. This one form a cycle in the tree. See, this one form a cycle, which is V5, V4, V7, V8. Okay, so this cannot be added. Okay, and the next one will be weight 7, next edge, and this is fine. It doesn't form any cycle. Okay, and then it's 8, but this 8 we cannot add, because when we add this edge, we form a cycle, which is V9, V3, V2, V1, V6, V7, V4, V5. They're already connected, okay? So the last edge to consider is this one, and it's still already connected. Okay, so the blue edges, it connects to all the nodes, and this is the spanning tree that we output. Okay, so that's how the algorithm works. Okay? Questions? I just okay. All right. Now, well, but to implement this idea, what we just went through, okay, what did we say? I'm going to sort all the edges first by their weights from small to large. Okay, this is no problem. We know how to sort. We talked about sorting at the beginning of this class. Okay, then I'm going to inspect all the edges one by one. Okay, and when I but every time I add a new edge, so and I also maintain the minimal current edges in the minimal spanning tree that you already found. Okay, those are the blue edges during the course. Okay, now what do we need is that when I inspect the new edge EV that I want to add, I need to check, does this EV form a cycle in the existing partial tree we already computed or not? Okay. This is in the collection of edges we added so far, basically in the existing partial tree we already computed. We need to be able to check whether this edge is valid or not, whether it forms a cycle or not. Okay, so how do we do that? Okay, and let's assume that we have a way to do this, and I'm coming to this in a minute. Okay, so in fact, okay, let me come back here. So let's say that at some point that I want to add the edge UV. Okay, and at this point, you already computed a bunch of edges that you output as a minimal spanning tree. Okay, maybe these are the edges you already computed. Okay, then the question is that does the addition of edge UV form a cycle with all the other blue edges? That's what we want to ask. Okay, and what does this mean? Really, what this means is that note that UV will form a cycle if U and V are already connected by the blue edges. Okay, in particular, if I already have edges like this to connect UV, okay, so I already have this blue way to connect the UV. When I add this yellow edge UV, then clearly I form a cycle, which is simply the concatenation of this blue path with this yellow edge. Okay, so in that case, UV will form a cycle. Okay, but if U and V were not connected by the blue edge, okay, let's say that I don't have this edge here. Okay, so at this point, U and V are not yet connected by the blue edge, then adding UV will not form a cycle very clearly, because that was the only way to connect UV. In other words, U and V was not connected before. This new edge is the only way to connect them. Okay, so in other words, what we want to test in order to know a new edge UV add a cycle or not, what we want to check is that are the nodes U and V already in the same connected components in the blue, among the blue edges or not? Okay, so you look at the collection of edges that we've already found so far, or the blue edges. If U and V are in the same connect components, that means that they are already connected by some blue paths. Then adding UV, this yellow edge would form a cycle. Okay, if not, then they were not, and adding UV will not create a cycle. That's it. Okay, so this become a test of checking whether UV are in the same connect components or not. Okay, so this is I hope it's clear. So checking whether UV is valid or not, namely whether they create a cycle or not, becomes just check whether nodes U and V are in the same connect components in the collection of blue edges we add so far or not. Okay, that's it. Okay, all right. So with this, here is a high level outline of the Kruskal's algorithm. Okay, let's look at it again. We're given the graph, and we're going to compute the minimal spanning tree, which is just going to be, we treat that as, the node set is still the same as the input node set V of the graph, okay? And then we're just inserting edges for that. We need to find the V minus 1 number of edges, okay? So the first step, we simply sort all the edges by their weights, okay? From small to large, okay? Next, we look at the edges in this sorted list one by one from small to large, okay? Every time I have a new edge UV to inspect, what do? I check, are U and V already in the same connected components in this partial tree, the partial collection of the edges I found for minimal spanning tree already, okay? So if it's already in the same connect components, that means this U and V already connected in my output. Okay, that means that I shouldn't add this edge because it would form a cycle. Okay, but if it's not, that means that U and V are not yet connected. U and V, right? This edge UV right now is my cheapest way to connect a new to reduce a component, to merge two components. Okay, so in this case, I simply added this edge to my output graph minimal spanning tree. That's it. Okay. That's the algorithm. All right. So the outline is very simple. Okay. What do we need? Sorting, we know what to do. Okay. The only thing that we need now is to have a way to check whether nodes U and V are in the same connected components in the current minimal spanning tree or not. Okay, now if you think about it, do we know how to do this? Well, the current minimal spanning tree is basically a partial graph, right? I mean, it's basically all the blue edges we found so far, okay? And you are given this graph, if I ask you, are U and V connected? How fast can you check for that? Okay, so I mean, if you're watching us, just think about this for a second. Okay, all right. Then we actually already seen how to do connectivity. Okay, to check whether U and V are connected in this graph and minimal that we computed so far, we just need to do any graph traversal algorithm, graph search. You can do BFS starting from U and then see right now in MST this graph whether we can reach V or not. Okay, and that is a valid solution, but it's not the most efficient one. Okay, so that you can. So this step can be implemented using any graph search strategy, say BFS on source U. Okay, you can just run BFS on source U, see whether you reach V or not on the graph minimal spanning tree. So you check in this graph starting from the source. Okay, so this can be done this way. Okay, but remember that the BFS takes time linear to the size of the graph. Okay, that means that if I do it this way, then this step is going to take order of V time. And since I have a for loop of, I have to go through all edges, then the whole time will be V times E, which is not very efficient. Okay, so this is the first approach, but it's not very efficient. Okay, and it turned out that we're not going to talk about this in this class, but it turned out that in this particular case, because we're changing the minimal spanning tree, we actually have a lot of control. You don't have to rerun BFS every time, because every time compared to the previous tree, your size just increased by some newly added edge. Okay, so you can actually maintain a data structure, and this data structure is called unifying data structure. So the unifying data structure is a standard data structure that lets you efficiently test whether to maintain the connect components information as you add more and more edges. Okay, so it's standardly it's some called a maintaining dynamic set. Okay, as your set merge and then they have dynamic operations. Okay, but at any rate, the bottom line is that using the unifying data structure, okay, we can then perform this in the same component operation efficiently. Okay, and in fact, this can be done instead of remember using BFS, I have to spend linear time here, but using unifying data structure, then this step can be achieved in log of V time, so-called amortized time. Okay, and of course, and the total time complexity as such becomes because this step has to be done E time. Okay, so this becomes, in fact, this should be V plus E log V. Okay, time. Okay, and if the input graph is connected, this is simply E log V. Okay, all right. So the key here is that to know the high level framework of Kruskal's algorithm. Okay, you don't need to know that how we really implement this check and connect components, but we need to know the high level. Here's how the algorithm runs. It sorts all the edges and add them one by one while checking whether every edge we want to add from a cycle is valid or not. Okay, if it's not valid, sort it out. If it's valid, we output it added it to the partial minimal spanning tree we are maintaining. Okay, so that's the first thing the key takeaway message from this. The second one is that know that if we're going to use the so-called unifying data structure, then this can also be implemented efficiently. Okay, in time V plus E log V. which when the graph is connected, is simply E log B time. Okay, so that's what we what you want to keep in mind from this slide. Okay, all right. Okay, so